Well, hello there. Today we are talking about mass energy equivalence and binding energy. Now, here's a question for you. Do you find yourself to be less interested in the sun over time? Is your attraction to the sun dwindling? Well, technically, yes. The force that attracts you towards the sun is the force of gravity, and we know that Fg, wait for it to load, we got it, Fg is equal to G m1 m2 over r squared, where m would be the mass of you, m2 would be the mass of the sun, and r is the distance between you guys. Well, here's the truth, is that the mass of the sun is slowly decreasing over time. And when I say that it's slowly decreasing over time, I mean it's very quickly decreasing over time. If every man, woman, and child in Denver had a Honda Civic, and we took all of those Honda Civics and we put them all in a giant pile in the park, the mass of all of those Honda Civics would be the amount of mass that is leaving the sun every second. Another way to think about it is if you had 1,000,000 large elephants, not small elephants, but go to the zoo and find the biggest elephant that you can find. If you had 1,000,000 large elephants and you put them all in the park together, there would be 1,000,000 large elephants leaving the sun worth of mass every single second. There are about 4.5 billion kilograms of mass leaving the sun every single second. Where is all this mass coming from? It's coming from the sun's energy. The sun has so much energy and it puts out so much energy because it's turning its mass into energy. So every second on the sun, 4.5 billion kilograms becomes energy. And that energy is energy that runs, well, our entire planet. Now, here's the thing, is some students start to get concerned here and they say, wait a second, Miss Wilson, you're saying 4.5 billion kilograms is leaving the sun every second. Should we be concerned about this? Slightly, but also we still have enough mass on the sun for it to last another 4.5 billion years or so. So I think we're probably going to be okay for a little bit here. This concept of mass becoming energy is what we call mass energy equivalence, and it's our topic of the day. Today, we'll talk about Einstein's most famous equation, E equals mc squared, and what that really means. Let's go ahead and take a look. I'm going to pause this, clear us out, and then we'll take a look at E equals mc squared. Whew, I am glad I hit pause there because you will not believe the technical difficulties that we just underwent. Don't try to change your pen color to purple. That's all I'm going to say. Okay. Here's this famous equation from Albert Einstein, E equals mc squared. Now, this is an equation that you probably know because just about everybody knows this equation, but not a lot of people know what this equation means. Here we have E. E stands for energy. Here we have mass. I've actually written it as a delta mass because it's going to represent a change in mass. Change in mass. And here I have c, which some people have said the only c I know is the speed of light. That's what this c is. It's the speed of light, 299792458 meters per second. And we all know that the speed of light is a constant. Well, here, looking at this equation, some people who are not physics people might say, okay, if you take mass and you make it go as fast as the speed of light squared, then you get energy. And that's not true. That's not what this equation means. What this equation means is that mass is energy. And if you want to know how much energy that mass is worth, take that mass, multiply it by the speed of light squared, and that gives you energy. It also means that energy can be mass. And if you want to know how much energy is mass, you take that energy, you divide it by c squared, and you get how much mass that energy is worth. This is a statement of mass energy equivalence. It means that energy and mass are the same thing. You can imagine why this equation was kind of a crazy equation at the time and is still a crazy equation today. You could imagine why it would get so famous so fast. Because this equation says that energy and mass are the same. That energy and mass are two different versions of the same stuff. This is completely contrary to everything that we've ever taught or understood about energy and mass. We talk about energy as being one set of stuff and mass as being another set of stuff. But Einstein says no. They're the same deep down. He says that if you have mass, that is kind of like, not really, but it's kind of like congealed energy. And you can use energy to make mass. Now, this was totally, you could imagine, and still is totally like revolutionary for the way that we see all of physics. Let's do this. Let's see how much energy would a penny be worth. If I could take the mass of a penny and I could turn the mass of a penny into energy, in other words, just like how all the mass from the sun is disappearing because it's all going to energy, what if I could take that penny and I could turn all of its mass into energy? How much energy would that little penny be worth? Well, here's what you would have to know. You'd have to know that the mass of a penny is very small. It's about 1 gram. So it's 0.001-ish kilograms. I'm going to take all that mass, and I'm going to start with that amount of mass, but then I'm going to end with no mass because I'm going to turn all of that mass into energy. We know that C is equal to 299792458 meters per second. And finally, we're looking for how much energy would we get out of this penny. Well, if I wanted to know how much energy I would get, I would use E equals mc squared. E is equal to delta m times c squared. My m here is 0.01 kilograms. My c, you know, is 299792458 meters per second squared. Plug that into your calculator, and you get about 9 times 10 to the 13th joules. That is a lot of energy. In fact, that's about the amount of energy that was released from the bomb that dropped on Hiroshima. Serious amounts of energy, all from one tiny penny. This c squared means that just a little bit of mass is worth a lot of energy. And here's the idea. If we could somehow find a way to turn mass into energy, we would have so much energy. And that's the idea of nuclear fission and nuclear fusion. But more to come on that later. The main story for today is that a little bit of mass is worth a whole lot of energy. You can turn mass into energy, but you can also turn energy into mass. Did you know that a melted ice cube has a mass that is slightly different than that of a frozen ice cube, a solid ice cube? Why? Because you put in a little bit of energy. And when you put in a little bit of energy, some of that energy actually becomes mass. So a little bit of the energy that you put in becomes mass of the ice, and the melted ice has more mass than the solid ice. Crazy stuff. This is like real life stuff, not like made up stuff. Real life stuff here, that your ice has different masses depending on whether it's melted or solid. This is the concept of mass energy equivalence. What we're going to jump into next is we're going to talk a little bit about binding energy. Binding energy, well, actually, I'm going to pull up a new tab here, and then we're going to define it, and then after that, we'll look at some examples. One sec, let me get a new tab. Okay, here we go. Let's talk about binding energy. Here in my hand, I have, wait, can you see this? How do I let you see this? Here in my hand, I have a bunch of marbles. Now pretend that these marbles are not marbles. Let us pretend that they are protons and neutrons, and they are stuck together in the nucleus of an atom. Okay. All of these protons and neutrons are held together by what we call the nuclear strong force. If I wanted to take one of these protons off the nucleus here, I would have to take my fingers in here, grab it really, really tight and pull it off. And it would take some energy to do that. This thing wouldn't just go, okay, easy peasy. No, it's held in there by the nuclear strong force. If I try to take this thing off, I'm going to have to put in a whole lot of energy to get this thing ripped off the rest of the nucleus. The amount of energy it takes to pull a nucleus apart, to take each little proton or neutron and pull it out of the nucleus, the amount of energy that takes is what we call the binding energy. We call it the binding energy because it's the energy that binds together all the protons and neutrons in the nucleus of the atom. The binding energy, you can think about it as how much energy it would take to pull that little nucleus apart one by one. So, here's a definition for you. Is binding energy of the nucleus is the amount of energy it would take to pull that nucleus apart. The binding energy of the nucleus is the amount of energy it would take to pull that nucleus apart. The binding energy of the nucleus, one more time, is the amount of energy it would take to pull that nucleus apart. Okay. Now here's a thought for you. If I wanted to pull out just one of these little protons right here. Oh, sorry, I made this small, and now I'm going to make it big again. This is just, I know, I'm the worst. I'm absolutely the worst. Okay, here we go. If I wanted to pull one of these little protons out of the nucleus, I have to reach in with my tweezers and pull with tons of energy. And I have to apply a force over a distance. I have to do work. I transfer energy into this little guy right here. And then I set him off to the side. Hey, now I have one little proton off to the side. And then the rest of the nucleus is over here. If I have one little proton off to the side, I had to put in energy to get this little proton all by itself. Where is that energy now? It turns out the energy is now stored inside this little proton as mass. Check it out. I put in energy to pull it out. The energy gets stored in the proton, and the proton becomes more massive. It gains more mass from the energy that I put in. This is what I mean when I say that it gains mass. What I mean to say is that a proton, when it's outside of a nucleus, has more mass than a proton that's inside the nucleus. You say, what, Miss Wilson, for serious? Yes. A proton has different mass depending on where it is. And same thing with a neutron. And same thing with an electron. A proton has more mass when it's by itself than when it's in the nucleus of an atom. And in some atoms it has more mass, and in other atoms it has less mass, depending on how stable or unstable the nucleus is. If it's really easy to pull it apart, well, then that means you don't have to put in that much energy in, which means it's already pretty massive. But if it's really hard to pull apart, then that means that most of its mass, or not most of its mass, but a lot of its mass went towards the energy of binding it together with its friends. And so that is a very, very small proton in a very, very stable nucleus. But in an unstable nucleus, it's a little bit less massive, and in an unstable nucleus, it's a little bit more massive, and it's easier to pull off. So, here's the thing. A proton has different amounts of mass depending on where it is. If it's in the nucleus, if it's bound up together with its buddies, it has less mass. And if it's out sitting all alone, then it has more mass. If you look at the mass of a proton, now I can shrink this down. The mass of a proton that we say is unbounded. It means just a free little proton sitting all by itself. Here we go. Mass of an unbounded proton. The mass of an unbounded proton is 1.0072 76 46 688 units. And the mass of a proton in carbon is 1.000, let me get this right, 0.0000 atomic mass units. Check it out. The mass of an unbounded proton has more mass than a bound proton. That extra mass, where does it come from? It comes from energy. The amount of energy that is the binding energy becomes mass. So if you wanted to know what the binding energy was, you could just take this extra mass, and that change in mass, the difference in mass between here and here, is the binding energy. So when a proton is bound up, it has less mass. When it's all by itself, it has more mass because you have to put in energy to separate it from its friends. And when you put in energy, that energy turns into mass. Hey, let's talk about units really quick because we got a funky units thing going on here, and we got a few units that we got to address. The first unit that we need to address is these like atomic mass units here, and then we also have to address a type of unit that we call the electron volt. So I'm going to change up my color really quick here. Let's go to a light purple. I'm going even lighter. I'm going crazy light. Let's talk about our units real quick. We'll see if my undo button works. Please work. Yes? Maybe? Yay! The undo button was not working before. So, anyway. Okay, here we go. Let's talk about units. Units. The first thing that we are going to talk about is an atomic mass unit. One atomic mass unit, which we represent by the lowercase letter u, here's the problem, is that the mass of a proton, well, it depends on whether it's bounded or unbounded, but the mass of a proton in carbon, we'll start there. The mass of a proton in carbon is 1.6605 times 10 to the negative 27th kilograms. That is the mass of a proton. Well, all the good people of the world got mass of a proton in carbon. I'm going to write that down somewhere. This is a proton in carbon. Okay. Well, all the good people of the world got very, very tired of saying 1.6605 times 10 to the negative 27th kilograms. 1.6605 times 10 to the negative 27th kilograms. 1.6605 times 10 to the negative 27th kilograms. And we said that's a long use of our words and our time. So they said that is kind of an obnoxious way of talking all the time. What if we defined a new unit, and this new unit is based on the mass of a proton? But they said, which mass of a proton are we going to use? Are we going to use the mass of an unbound proton? Are we going to use the mass of a proton in carbon? Are we going to use the mass of a proton in lead? Are we going to use the mass of a proton in uranium? Are we going to use the mass of a proton in helium? So they decided after much debate that they would use the mass of a proton in carbon, and that has become the standard. So one atomic mass unit is the mass of a proton in carbon. And so it's a shorter way to talk about the mass of a proton in carbon because this is kind of a long and difficult way. But look, if we just made that number 1, nice and easy. So you can see up here that the mass of a proton in carbon is 1, but the mass of an unbound proton is slightly more than the mass of a proton in carbon. So that's a little bit on our units of mass. Let's talk a little bit about our units of energy. So far, we have used units of energy that are joules, and joules are totally helpful to us and totally great. But when it comes to these kinds of things, we actually have another unit of energy that we use often, and that unit of energy is what we call an electron volt. An electron volt is the amount of energy it would take to move one electron through 1 volt of potential difference. So if I had two plates over here, if I had a negatively charged plate over here, and a positively charged plate over here, and this plate was connected to the positive end of a battery, and this end was connected to the negative end of a battery like this, and I had a little electron right here. Doop. If this battery was providing 1 volt of potential difference, so in other words, the difference between the high potential place here and the low potential place here was 1 volt, then you agree it would take some energy. I'd have to grab this electron and move it against its will, and I would have to grab this electron and pull it over this way. The amount of energy it would take to move this 1 electron through 1 volt of potential difference, that is what we call 1 electron volt. And we can define it this way. We say that the change in potential energy here would be going from low potential to high potential. The change in potential energy is equal to, that U looks a little V-ish. You know, I mean U here. The change in potential energy would equal delta VQ. You remember this equation, yes? Where delta V is the potential difference between here and here, which would be, in this case, 1 volt. And Q is the charge on an electron. It's 1.602 times 10 to the negative 19th coulombs. 1.602 times 10 to the negative 19th coulombs. So that means that 1 electron volt, the amount of energy it would take to move this electron from here to here, is equal to 1.602 times 10 to the negative 19th joules. So oftentimes, we will use atomic mass units instead of kilograms, and we'll use electron volts instead of joules, where 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. There's a little note on units. Let's go ahead and try a practice problem. I'll go ahead and clear out our board here. Okay, here's our practice problem. We are going to calculate the mass defect and the binding energy of a helium nucleus. We're going to take this problem as 2 parts. First, we're going to calculate the mass defect, and second, we're going to calculate the binding energy. So I'm going to do this almost like this is our part A here, and this is our part B here. Now, when we do this, let's talk a little bit about what this problem means. A helium nucleus has, or the one that we'll look at, has 2 little protons and 2 little neutrons that are all bound together in a little nucleus. Now, here's what we're asking for when we're asking for mass defect. We know that each of those little protons and each of those little neutrons would have more mass when they are outside of the nucleus than when they're in the nucleus. The mass defect is how much mass do they lose when they all enter into the nucleus together. Here's how we'll do this problem. First, we have to start by writing down our knowns and unknowns. To do this, you will likely need to look in your textbook, and you'll also probably need a periodic table. If you look in the very back flap of your textbook, you'll see that there's a whole table of constants here. If you look where it says useful atomic data, then it has things like the mass of a neutron and the mass of a proton and other numbers that might be helpful for you. So, here's what we're going to do is we're going to look at that back flip and we're going to write down some things that are useful to us. First, it is going to be useful to know that the mass of a proton by itself, the mass of an unbounded proton, which is essentially, do you agree, the mass of a hydrogen atom, is equal to 1.0078, we got it, 25 units. And you can find that on the back flap. Then, wait, I'm trying to see. I think that there's another spot in the appendix. Wait, let me check this page number really quick and I'll get back to you. Okay, then if you look on the back flap, you'll find that the mass of a neutron is equal to, let me look at mine, 1.00865 atomic mass units. And then finally, we want to know the mass of a helium atom. If you look in your textbook has a little appendix on page 874. And here you can see it has, like this, it has an abbreviated table of isotopes and atomic masses. And so it tells you all of the different atomic masses for like little different isotopes of different elements. So if you look on the table and you go to number 2, which is helium, then it shows you all the different masses for all the different types of helium. We're going to look at the mass of helium that is for the fourth one, which has 2 protons and 2 neutrons. When you look at that mass in that table, it tells you, do you see where it says atomic mass there? It's the 1, 2, 3, 4, 5th column over. It says that the mass of a helium nucleus is 4.00262 atomic mass units. And we're looking for what's the difference in mass between when these little protons and neutrons are out by themselves versus when they're bound up together in a helium atom. We're looking for the delta M, the difference in mass. Now here's how we're going to do this is we're going to do this problem in 2 parts. The first part is that we are going to find the delta M, and the second part is that we got to do a unit conversion to get it into kilograms. So let's go ahead and try. For step 1, we're going to find the difference in mass. To find the difference in mass, I start by saying that delta M, the difference in mass, is going to equal the mass of the parts minus the mass of the whole. That's always true because the mass of the parts are always going to have greater mass than the mass of the whole. When I plug in the mass of the parts here, I have to look at all the different things that I have. For all the parts of a helium nucleus, I have 2 protons and 2 neutrons. So to find the mass of the parts, I'm going to add together the mass of 2 protons, 2 times the mass of a proton, plus the mass of 2 neutrons, 2 times the mass of a neutron. And then I'm going to subtract the mass of the whole thing. The whole thing is the mass of a little helium atom, like this, or a helium nucleus. Then I plug in numbers, and I'm going to give myself a little bit of space here. When I plug in numbers, I get 2 times the mass of a proton, which I have is 1.0078825 atomic mass units, plus 2 times the mass of a neutron. A neutron we have over here is 1.0086665. That says 8665. It's very, very difficult to read, but it's there. And then I'm going to add all of that together and subtract the mass of a helium nucleus. The mass of a helium nucleus we know is 4.002602 atomic mass units. Somehow one of my zeros just died. Okay, there we go. This now has the mass of the parts being added together. This is the mass of 2 protons plus the mass of 2 neutrons minus the mass of everybody when they're combined. And if you plug that into your calculator, we get a difference in mass of 0.0. Do you need to keep a lot of decimal places here? Yes. Please do a good job taking care of your sig figs. 0.0303. Sounds like the beginning of a great phone number. 78 atomic mass units. Okay, that is step 1. Step 1, I'm going to change my color up here just a little bit so that you can see it. Step 1 is to find the difference in mass. Step 2 is going to be to then convert that difference in mass into kilograms. Do you see how right now the difference in mass is in atomic mass units, which is totally great unless we want to see how much energy it's worth, and then in order to do that, we're going to have to get it into kilograms. So for step 2, we're going to convert it into kilograms. Let's go ahead and try. Here's what we say. We say that the change in mass in kilograms is going to equal, we'll do a little unit conversion here. We're going to go from 0.03038 atomic mass units. Then to go from atomic mass units to kilograms, we have to remember that 1 atomic mass unit is 1.6, oh, I don't want to mess up this number, 6605 times 10 to the negative 27th kilograms. That's a negative 27, by the way. Plug that into your calculator, and you get that the difference in mass is 5.0. I might have to shrink this down a little bit. Well, okay, that's as small as it can go. I'm going to move this up a little bit. There we go. Okay, 5.0443 times 10 to the negative 29th kilograms. And that is our mass defect. And we are done with part A. Part A asks us to calculate the mass defect. That means that when two protons and two neutrons come together to form a helium atom, they lose 5.0443 times 10 to the 29th kilograms. Where does that mass go? Well, that mass becomes energy. So the question is, how much energy is that? And that would be the binding energy of the helium nucleus. And that's the second part of this problem. I'm going to go ahead and grab one new tab. 1 second. Okay, for part B, we're asked to calculate the binding energy. Here's the idea. To calculate the binding energy, we're going to take that mass and we're going to use E equals mc squared to figure out how much energy that mass is worth. Now, this is also going to happen in 2 steps. In one step, we're going to calculate the energy, and in the next step, we're going to do a unit conversion to get it into electron volts. Let's go ahead and try it. Here's where we start. We start with, to find the binding energy, and you would write down all your knowns and unknowns here, but I'm just going to assume that I already had them written down from the page before. Delta E equals, whoa, that is not what I meant to do. Okay, back. We can say that the change in energy is going to equal the change in mass times c squared, because as much as the mass defect is, that's how much the energy is going to change. That's how much binding energy there will be. So now here's what I do. I take the mass, the one that I just found in kilograms, and I'm going to multiply it by c squared. The mass that I just found in kilograms is 5.0443 times 10 to the negative 29th kilograms. And now I'm going to multiply this by c squared. C is 299792458 meters per second. And we'll square that. Plug it into your calculator, and you get 4.5336 times 10 to the negative 29th kilograms. Whoa, no. Oh, bad. I was just copying from above. I was doing a bad job. So sorry, team. Try again. Times 10 to the negative 12th joules. Now you say, Miss Wilson, that doesn't seem like that much energy. But let's see how many electrons we could move with this amount of energy. Here's what we're going to do. We're going to convert this into electron volts. We say that if we want, we're going to convert this from joules into electron volts. If I want to know the change in energy in electron volts, and actually I'm going to go all the way up to mega electron volts, because as you'll see, talking in terms of electron volts is going to be a crazy number. The way that I'm going to do this is I'm going to take 4.5336 times 10 to the negative 12th joules. And I'm going to say, hey, listen, there are, we know, if we're going to electron volts, we put joules on the bottom here like this. We know that for every one electron volt is worth 1.602 times 10 to the negative 19th joules. That says negative 19th, by the way. But then as you're going to see, we're going to get kind of a ridiculous number here. So I'm just going to go ahead and convert these electron volts into mega electron volts, which is going to be, you're going to see mega electron volts a lot because an electron volt actually isn't that big. When we do this unit conversion, we know that one big mega electron volt is equal to 1 times 10 to the 6th little electron volts. Go ahead and plug that into your calculator, and you get 28.30 mega electron volts. That is a lot of electrons that you could accelerate through 1 volt of potential difference. And that is then your final answer. So you see, when we do these problems, we start by finding the mass defect by doing the mass of the parts minus the mass of the whole. Then we convert it into kilograms. Then we find the binding energy using E equals mc squared. Then we convert it into electron volts or mega electron volts using our unit conversions. And that's how you find the binding energy. This is how much energy you have. This is the binding energy of a helium nucleus. The easiest way to think about it is if you wanted to pull a helium nucleus apart into all of its constituent parts, it would take you 28.30 mega electron volts to do it. And that, ladies and gentlemen, is the bell. And with that, we shall be ending our virtual class today. I hope you have a wonderful rest of your day, and I'll see you next time. Bye, good people.